Hello and Assalamualaikum everyone. My name is Amira Nuraisha binti Salihin and I'll be presenting PHY568 Electricity and Magnetism. First and foremost, we will go through vector analysis. This topic have vector addition, subtraction and multiplication, coordinate system and its transformation, distance between 2 points, vector calculus, del operator, gradient of scalar field, divergence of vector, curl of vector, Stokes theorem, and the Laplacian. Vector analysis is a mathematical tool with which electromagnetic concepts are most conveniently expressed and best comprehended. In this topic, a quantity can be either a scalar or a vector. Scalar is a quantity that has only magnitude, quantities such as time, mass, and energy, while a vector is a quantity that has both magnitude and direction, which are displacement, velocity, and force. Unit vector using this equation where A bold is a vector of A and modulus A is the magnitude of vector. The magnitude of vector represents how strong or large the quantity is, for example, speed or force strength. Vector component allows us to break vector into parts along the x, y, and z direction, making the calculations easier. Next is vector addition and subtraction. For example, given two vectors at point A and point B, vector addition combines two vectors to produce a resultant vector considering both magnitude and direction, while vector subtraction is equivalent to adding a vector with the opposite direction, which is the minus operation. Both of these operations are important in physics to determine net force, displacement, or field at a point. Vector multiplication consists of dot product, cross product, and also triple product. Dot product will produce a scalar quantity and is used to determine how much two vectors align with each other, and the results are also called as scalar product. If A and B are said to be orthogonal with each other, A dot B equals to 0, meaning they are also perpendicular. The cross product produces a vector quantity and is commonly used to find torque and magnetic force direction. The result of cross product will be in vector quantity. There are two types of triple product, which is scalar triple product and also vector triple product. Both of these equations can be seen below. Next is coordinate system. There are three coordinate systems in this topic, which is Cartesian coordinate, cylindrical, and also spherical coordinate. The Cartesian coordinate system uses x, y, and z axes and is suitable for rectangular geometries, while cylindrical coordinate use rho, phi, and also z. For spherical coordinates, they are best used for spherical objects like point charges or charged spheres and use r, theta, and also phi. Coordinate transformation allows us to convert one coordinate system into another for easy analysis. For example, Cartesian to cylindrical using this equation, Cartesian to spherical using this equation, cylindrical to Cartesian using this equation, and last but not least, spherical to Cartesian using this equation. Distance between 2 points formulas differ depending on the coordinate system used, but the main equation is this one. In Cartesian coordinates, distance depends on changes in x, y, and z values, while cylindrical and spherical distance formulas are adapted to circular and spherical geometries. In vector calculus, there are three differential elements that are very important, which is displacement, surface, and also volume. For differential displacement in Cartesian coordinate, we can see in this formula, which shows that it is moving in x direction, y direction, and also z direction. Let's look at the differential normal surface for Cartesian coordinate, where I will take this as an example. For this one, it's only moving in the direction of y and also z. The x will equals to 0, so that's why they are not written here, and that's why the vector is ax. Same goes with the cylindrical coordinates and also spherical coordinates. The del operator, written as inverted triangle, is the vector differential operator. This is the equation in Cartesian coordinates. The vector differential operator, otherwise known as the gradient operator, is not a vector in itself, but when it operates on a scalar function, for example, a vector unused, the operator is useful in defining the gradient of scalar, the divergence of a vector, the curl of a vector, and the Laplacian of a scalar. Gradient of scalar field shows that the direction of maximum increase of that field. Its magnitude represents how fast the scalar quantity changes. In electrostatic, the gradient is used to relate electric potential to electric field. And these are the equations in Cartesian coordinate, cylindrical coordinate, and also spherical coordinate. As for the divergence of vector, it measures how much a vector field spreads out from a point. A positive divergence indicates a source, while negative divergence indicates a sink. Divergence of vector can also be written as inverted triangle dot with A. Divergence theorem relates surface integrals to volume integrals. It states that the total outward flux through a closed surface equals the volume integral of divergence, and this is the equation. Curl of vector states that a rotational vector whose magnitude is maximum circulation of A per unit area as the area tends to be 0 and whose direction is the normal direction of the area when the area is oriented to make the circulation maximum. In conclusion, curl measures the rotational tendency of a vector field. The direction of curl follows the right-hand rule, and curl of vector is important in analyzing magnetic fields and fluid motion. And as we can see below, there are equations for its Cartesian, cylindrical, and also spherical coordinate. Next, Stokes' theorem states that the circulation of vector field A around a closed path L is equal to the surface integral of the curl of A over the open surface S bounded by L provided that A and curl of vector A are continuous at S. Curl of vector A is also known as inverted triangle cross with A. And these are the equation, and this is the final equation of Stokes' theorem. Last but not least in this chapter is the Laplacian. Laplacian is the divergence of the gradient of a scalar field. It indicates how a quantity diffuses or spreads in space. It also can be written as inverted squared A, which we will differentiate the divergence 2 times to get the Laplacian. Next, we will go through second topic, which is electrostatic field. This topic consists of Coulomb's law and electric field intensity, electrostatic fields, electric flux density, Gauss' law, Maxwell equation, electric potential at location R, relationship between E and B, and the current density. First and foremost, Coulomb's law. Coulomb's law is an experimental law formulated in 1785 by the French colonel Charles Augustin de Coulomb. This law states that the force of between 2 points charges Q1 and Q2 is a long line joining them, directly proportional to the product Q1, Q2 of the charges, and inversely proportional to the square of the distance r between them. This is the equation for Coulomb's law, where K is the proportionality constant, Q1 and Q2 is the charges in Coulomb, R is radius in meter, and F is force in Newton. For electric field intensity, also known as electric field strength, is defined as force per unit charge when placed in the electric field. This is the equation for electric field intensity, where E is the electric field intensity, F is force, and Q is charge. Electric field intensity in the direction of F and is measured in Newton per Coulomb or volt per meter. And this is the electric field intensity at point R due to point charge located at R node. Electrostatic fields are produced by stationary charges. Different charge distribution creates different field pattern such as line charge, surface charge, and also volume charge. And these are the equations for electric field in line charge, surface charge, and also volume charge. While this is the electrostatic fields in infinite line charge and also infinite sheet of charge. Electric flux density represents electric flux per unit area. It also relates electric field to charge distribution such as point charge, line charge, infinite sheet of charge, and also volume charge. It is useful when applying Gauss' law, and these two are the major equations of electric flux density. For Gauss' law, it states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface. It simplifies electric field calculation for symmetric charge distribution. Gauss' law is also Maxwell's first equation. Electric potential is defined as potential energy per unit charge. It represents the work done in moving a charge in an electric field. Electric potential is measured in volts. This is the general equation for electric potential at location R. Electric potential at location R also have charge distribution such as point charge, line charge, surface charge, and also volume charge. Let us move on to the relationship between E and V. Electric field is the negative gradient of electric potential. This relationship shows how potential changes create electric field. It is derived using Maxwell's equation, which is Maxwell's second equation. Next is current density. The current through a given area is the electric charge passing through the area per unit time. Thus, in a current of 1 ampere, charges is being transferred at a rate of 1 coulomb per second. If current flows through a planar surface, the current density is in this equation. If the current density perpendicular to the surface, we use this equation. And if current density is not normal to surface, we use this equation. And if total current flow through surface S, we use this equation. Last but not least, in the second topic, we have two types of current density, which is convection current and also conduction current. As for convection current, it does not involve conductors and does not satisfy Ohm's law. It will occur when current flows through insulating medium such as liquid, gas, or vacuum. And this is the general equation. Second one is conduction current, which requires a conductor, where the conductor will provide conduction current due an impressed electric field. And this is the final equation. The last part is Maxwell's equation. In this part, we have time-varying field, Faraday's law, transformer and motional EMF, and also Maxwell's equation in the final form. In time-varying fields, we can see that stationary charges produce electrostatic fields. Steady current produce magnetostatic fields, and time-varying currents produce electromagnetic fields or wave. And these are the type of time-varying current: sinusoidal, rectangular, and also triangular. Faraday's law explains electromagnetic induction. According to Faraday's experiment, a static magnetic field produces no current flow, but a time-varying field produces an induced voltage called EMF in a closed circuit, which causes a flow of current. This principle is used in generators and transformers. For transformers and motional EMFs, the variation of flux with time may be caused in three ways: by having stationary loop, in a time-varying B field, or having a time-varying loop area in a static B field, or having a time-varying loop area in a time-varying B field. And this is the equation for VEMF. These are the equation for transformer and motional EMFs. First, we can see the stationary loop in time-varying B field, which is the transformer EMF. And these are the equation. Second is moving loop in static B field called motional EMF, and this is the final equation. Last but not least is the moving loop in time-varying field, and this is the final equation. Last but not least, I will explain Maxwell's equation in the final form. Maxwell's equation unify electricity and magnetism. They describe how electric and magnetic fields interact. And this equation form the foundation of electromagnetic theory. That's all from me, and I hope you enjoy watching this video. Thank you!